Hello everyone, welcome to this video of connecting the dots in physics. In this section 1.2, I want to emphasize the difference between the canonical momentum and the mechanical momentum. Canonical momentum is obtained by this equation dou L by dou Q dot, where Q dot is the generalized coordinate. So for a system with n degrees of freedom, we will have n number of generalized coordinate, and therefore we will have n number of corresponding canonical momenta, where this I now runs from 1 to n. Mechanical momentum refers to this product mass into q dot, where mass is mass and q dot is the generalized velocity. So if we have n number of generalized velocities, we will have n number of such mechanical momentum. Now these momenta are canonical momenta, which then we use to find out the Hamiltonian of the system, which is pi qi dot minus L. Note here that here we are using the summation convention, so this I actually runs from 1 to n, and this is the mechanical momentum. So in this section, we want to emphasize that these two kind of momentum may not be same for a system. To that end, what we will do is we'll consider three examples. The first example will be the problem which we left in last video, the ring rolling down an inclined plane. The second problem that we want to discuss is a charged particle placed in electromagnetic field. And the third example doesn't directly have the Lagrangian or Hamiltonian formulation in it, but it has a term of momentum which is not actually the mechanical momentum in the system. So before we begin directly with the topic, I wanted to consider, I want to derive the Lagrangian equation or Lagrangian of a particle which is moving in electromagnetic field. Let's first note that Lagrangian for a system is not unique. A system can have different Lagrangians. Some transformation can be made in a given Lagrangian, and that also can be one of the Lagrangian for the system. So this is the equation, Lagrangian equation of motion. Now if I consider this transformation where L is the Lagrangian of the system that we have calculated and L prime is a new Lagrangian, this L is basically kinetic energy minus potential energy. So to this Lagrangian, we are now adding this term df by dt. This f is a function of q and t. So it is function of all the generalized coordinates in general and time. And the only requirement for this f is that it should be differentiable. And now if we get this new Lagrangian by using this equation and put this L prime back into the Lagrangian equation of motion, we can easily show that the equation of motion is unchanged. For that, what we have to do, all we need to do is plug this new Lagrangian L prime into the equation of motion, which is dou L by dou Q dot minus dou L by dou Qi dot, this is I here, is equal to 0, but instead of L now we have L prime, which is given by this equation. To prove that this equation of motion is same as this equation of motion for the original Lagrangian, all you need to do is plug this right hand side in the equation. You will get some terms, and then you have to prove that terms which are added due to this second part df by dt in the original Lagrangian actually adds up to 0, and therefore everything that adds up due to this second term cancels out, and what you get ultimately is this is equal to d by dt of dou L by dou Qi dot minus dou L by dou Q dot. It's same as this equation. I am leaving this derivation as a PP, point to ponder. So this is going to be the first point to ponder for this video. Why we are discussing this derivation is because we will need this derivation when we considered the charged particle in external magnetic field. Let me erase the ink on the slide. Okay, so now let's derive this Lagrangian of a particle, of a charged particle in electromagnetic field. So let's start by considering one of the Maxwell's equation of electrodynamics, which is del cross E is equal to dou B by dou T. This equation is basically the differential form of Faraday's law of induction. Faraday's law of induction says that EMF induced is given by minus of dou phi b by dou t, where phi b is the magnetic flux, which is given by this integration b dot dA. This EMF here is integration over a closed loop E dot dl, where E is the EMF or electric field induced due to changing magnetic field, and this is equal to minus this integration, dou by dou t of integration b dot dA. Note here that this dA is area element, which is actually magnitude of the area that we are considering, and it is multiplied by unit vector perpendicular to the area, so that this dA becomes an vector. So EdL, now I can use Stokes theorem to write this line integral as integration over area, which can be done by considering this curl, and with this our equation then becomes del cross E dA is equal to integration of minus dou B by dou T integrated over area. This I'll write it as capital A, this is also capital A, which is the area element that we are talking about, and this is dot product here. So therefore now both of them are integrated over the area element, and we therefore can write del cross E is equal to minus dou B by dou T. So as I said, this basically is the Faraday's law of induction in differential form. If you are not familiar with Stokes theorem or these laws, I encourage you to get familiar with these topics. So we will start with this equation del cross E is equal to dou B by dou T. So this is the equation where we are starting. This is minus dou B by dou T. In the previous slide also that should have been minus sign. We then make use of the concept of vector potential. Vector potential is defined in this fashion: del cross A is equal to B. Why it is called vector potential is another story. If you don't know that, you can read that some other time. For now, just consider this equation as the definition of this A, which is called as vector potential, and let's continue with this derivation. So now what I'll do is I'll simply use the definition of vector potential, make some rearrangements to this equation. Del cross A is equal to 0. Now del here is a simple differential operator, and therefore it is independent of time, and we can write this equation as del cross E plus dou A by dou T equal to 0. Now what you see here is curl of a vector. This is the vector for which we are taking the curl, and that curl is equal to 0. Now if you take curl of gradient of some scalar, it is always equal to 0. Why? Because this is gradient of scalar field phi, which tells us how quickly this scalar field phi is changing with respect to space. It gives you the direction of maximum rate of change of phi with respect to space, and this curl is a quantity which tells us how a particular vector is being rotated. Now if del of phi is the maximum rate of change of phi, then it cannot curl around itself. Its curl should be 0 in that case, and therefore now by using these two concepts we can write this E plus dou A by dou T as gradient of some scalar field phi. Now since we already know that electric field E is given by minus del of V, where V is the electrostatic potential, we will use a minus sign here through that hand side. So V here is the electrostatic potential. Now we'll use this equation further to derive the Lagrangian for the particle in electromagnetic field. Next step now is to write down the force acting on a charged particle in electromagnetic field, which is Q into E plus V cross B. B is the magnetic field, E is the electric field. This first term QE is basically force due to electric field, and Q into V cross B is Lorentz force acting on the particle as it moves in external magnetic field. Now what I'll do is I'll use the electric field that we derived on the previous slide, E plus dou A by dou T is equal to minus of del phi, and therefore E is equal to minus del phi, this is a vector operator, minus dou A by dou T. F is Q into del of phi minus dou A by dou T plus V cross B is del cross A here. All I have done is use this E and put it back here, and similarly for this second term B I have written it as del cross A, where A is the vector potential, magnetic potential, and this equation then becomes F is equal to Q into minus del of phi minus dou A by dou T plus, now I have to find out this cross product. To this end, let's consider this equation. A cross B cross C is given by A dot C into B minus A dot B into C. Note here that this left hand side A cross B cross C is a vector quantity, and the same on right hand side we have this A dot C, which is a scalar, and therefore scalar multiplied by this vector is a vector. Similarly, A dot B is a scalar which is multiplied by C, which is a vector, and therefore right hand side is also vector. For our term now, V cross del cross A, this is equal to del dot V dot A minus V del and A. Dot sign is del cross del dot V dot A minus V dot or V into del dot A. So what I'll do is I'll separate the terms in this force with A, so this with del. So this is q minus del of, let's consider minus sign here itself, del of phi plus v dot a. So here I have used this term and this term, consider the del operator outside the bracket, minus the next term will be dou a by dou t plus v into del dot a. Let's continue with this force on the next slide. Let me write this force again onto this slide. So F is equal to Q into del, I have taken common, into minus of phi plus V dot A minus dou A by dou T plus, what's the next term, del V into del dot A. So this is closed. Now let's focus our attention to this particular term, which is dou A by dou T plus V dot del dot A. This term will is equal to dou A by dou T plus this V dot del is basically Vx, dou by dou x, plus Vy, dou by dou y, plus Vz, dou by dou z, and this is an operator which is then operated onto vector A, where vector A is axi plus, or let's keep this A as it is and see what we get. This is equal to dou A by dou T plus Vx into dou A by dou x plus Vy into dou A by dou y plus Vz into dou A by dou z. Note here that this whole term is vector because Vx, Vy, Vz, they are scalar components, and then we are taking differentiation of the vector with the scalars x, y, z. So it's basically a vector field, which should be a vector field given that the left hand side is also a vector. Vector potential A is in general a function of time and space, where r is xi plus yj plus zk, the position vector. So in general it is a function of t and r. This should be a vector, and if I change all these 3 or 4 independent variables on which a depends, so I change x, I change y, I change z, and we consider a at a different time, then what will happen is dA will change, and this change is given by this partial differentiation dou A by dou x into dx plus dou A into dou y into dy plus dou A into dou z into dou dz. This first term tells us how much A changes when you change x, because dou A by dou x is rate with which A changes with x, and then you multiply by how much x is changed. Similarly, this term gives you change that occurs in A due to change in y, and this term gives us change that occurs in A as we change z. But it may happen, since we are considering at different times, since we are changing all the 3 different variables, this A may change just because you are changing time. So I'll write it like this. Let me divide everything by dt infinitesimally. Let's erase all this dt. So I'm dividing the whole equation by dt, and this also is dt, where dt is tending to 0. So therefore this is nothing but x component of velocity, this is y component of velocity, this is z component of velocity, and therefore now if you compare this term and this term, they are same, and therefore I can write down the whole second term as dA by dt. So the force in the end is equal to q into del of minus phi plus v dot a minus this whole term, I can write it as dA by dt, the ordinary differentiation of a with respect to time. And now what we have, I'll again write down the force on the next slide. So F is equal to Q into del of minus phi plus V dot A minus dA by dt. Remember, why we are doing all this is because we want to find out Lagrangian of a charged particle in electromagnetic field. Here we have calculated the force which acts on a particle in electromagnetic field, and we are considering a general case where electric field and magnetic field both are changing. And now potential energy of such charged particle, I can calculate that using this definition of minus FdL or FdR, where R is infinitesimal small vector, small displacement, and then this potential of the particle inside the electromagnetic field is minus of, I'll take Q common, so it is integration, first I'll write this term, so it is now, oh, here also we should have a Q, it is common. This is del of this term minus phi, sorry, this is phi plus V dot A integrated over dr, this is the first term, minus the second term is integration dA by dt q into dA by dt. I think I have forgotten to write that q in the previous slides, please correct it, into dr. So let's first now concentrate on the first term. What we have is differentiation. This is actually, if I write that del operator, it will look like d dx of this whole term in the bracket integrated plus d dy of that term plus d dz of that term in bracket, dot product with dr, which is dxi plus dyj plus dzk, and this is equal to d dx of this term into dx, this is ijk here, let's not forget that del is a vector operator, plus d by dy of this term into dy plus d by dz into this term into dz, and then we are integrating it. So basically we are doing the inverse operations here. For the first term we are integrating it and we are differentiating, and therefore I'll erase everything, and therefore this potential V of the charge inside electromagnetic field is basically minus Q. Since we are performing this reverse operation, this integration and the differentiation, these will get cancelled and we will be left with minus, or minus, now this minus get cancelled, so it is, okay, let's write it as it is, minus phi plus V dot A minus this second term. Now I'll write it as df by dt. It is such that f is equal to integration q into a into dr, and most of you now must have realized that why we considered the invariance of Lagrangian under such differentiation. So potential energy finally we have is q into phi minus q into v dot a minus df by dt, where f is a function of r and t in general. All we need to do is use the definition of that Lagrangian as, sorry, it's not a vector, is equal to kinetic energy plus potential energy. Kinetic energy is half kinetic energy is half m into r dot square, where r is the position vector. R dot is basically x dot I plus y dot j plus z dot k. So it's a velocity in 3 dimension. Sorry, this has to be minus. Now for potential energy we can use this relation which we have derived here, which is going to be minus of q into phi minus q into a dot v plus some differentiation of function which is function of r and t. Let me check if I am correct. So therefore this is not kinetic energy, I have written the Lagrangian here. So Lagrangian of the charged particle is given by 1 by 2 m r dot square minus q into phi plus q into a dot v. Remember, in this equation r dot is the 3-dimensional velocity, phi is electrostatic potential, so this r dot is velocity, phi here is electrostatic potential, a is the vector potential due to magnetic field, and v is again velocity. So let me write this as phi square simply plus dou f by df by dt. This is ordinary differentiation, df by dt of this function r and t. So this is the Lagrangian for a charged particle in electromagnetic field. But now what I'll do is I'll make a transformation and I'll change the Lagrangian to L minus df by dt. So therefore L prime is equal to 1 by 2 mv square minus q into phi plus q into a dot v, and since I am subtracting df by dt and here I have addition plus df by dt, that is all, and instead of, now I'll get rid of that L prime sign and simply write L as 1 by 2 mv square minus q phi plus q into a dot v. So this is the Lagrangian of a charged particle in electromagnetic field. What has happened is, since we have got rid of this second term df by dt, what has happened is this dA by dt term, which is present here in the force, or which is present here in potential energy, now is absent, is not there in the equation that we have. This now is the second point to ponder for this video. There are only 2 points to ponder for in this video. Even when that term dA by dt. Now even when this term is not present in the Lagrangian that we have derived, does the Lagrangian equation of motion actually gives us the equation for force? How can you check that? You can use this Lagrangian which we have derived here and plug that into equation of motion, which is going to be like this, where x dot is dx by dt minus dou L by dou x is equal to 0. So this is the first Lagrangian equation of motion. Similarly, you will have equations for y and z. Now when you consider all these three equations, you should be able to reproduce the equation for force, which is q into E minus or plus V cross B, where E now is minus del of phi minus dou A by dou T. So this is the second point to ponder. What I want you to do is use this Lagrangian that we have derived, plug that into the equation of motion, Lagrange's equation of motion, and see if you can get the force accurately in terms of phi and A and Q, of course. This is the end of this video. We have successfully derived the relation for Lagrangian of a charged particle in electromagnetic field. This is the equation. I suggest that you derive both the points to ponder. These are the references that I have used: Classical Mechanics by Goldstein and Griffith's book for electrodynamics. This is the end of this video. If you are taking the add-on course on connecting the dots in physics, and if you have any queries related to this video, you can post them in the forum on the online portal. If you are not registered for the course and if you are watching this video on YouTube, you can put your queries or questions, or if there are any corrections, in the comment section. Thank you for watching this video.